Welcome to the Crazy Hat Chemist, and here we go in the 8th video of a series of 16. Today we're going to be talking about Gay-Lussac's law. So here we go. Gay-Lussac's law deals with gases at a constant volume. So the volume of constant volume. So the pressure of a fixed mass of gas is directly proportional to the absolute temperature, and you can see that on that graph right there. Pressure is proportional to temperature. We're going to get this equation right here. P1 over T1 is equal to P2 over T2. You should see that this is very similar to the combined gas law, and the volume is being held constant, therefore it's not in the equation. And you should also notice that the graph for the Charles law and the Gay-Lussac's law is very similar. And that is it. They're both direct relationships, unlike Boyle's law, which is an inverse relationship. Just make sure you know that. Okay, so here's an application of Gay-Lussac's law is a pressure cooker. So what is occurring to the pressure as the temperature increases with constant volume? So as a pressure cooker, what happens in a pressure cooker? And that is the temperature goes up, the boiling water, the gas of that boiling water has nowhere to go except to stay in that container. So the pressure builds up. As you increase the pressure, then you increase the temperature, and that's why things cook in a pressure cooker much faster, because it's actually at a much higher temperature. All right, so as always with these kinds of problems, I want you to make a prediction as to which direction this process will be occurring. So with this law, Gay-Lussac's law, the volume is being held constant. So on this piece of wood right here, we're going to rotate at the volume because the volume is being held constant. So as you follow those two arrows, as the temperature goes up, the pressure goes up. And also, just like this, the temperature goes down and the pressure will go down. So it is a direct relationship with Gay-Lussac's law. All right, let's do a problem. Okay? So, gas calculation number 6. If a half-full cylinder of propane gas at 92.5 kilopascals and 72.8 degrees Celsius is filled completely until the pressure is 2.2 atmospheres, what is the temperature of the cylinder? So what we need to do is we need to make sure that our two pressure units, that is kilopascals and atmospheres, are in the same set of units. So we're going to make that calculation first. We're going to convert the atmospheres into kilopascals this time. 2.2 atmospheres has two significant figures. I'm going to maintain two significant figures with the answer of after this conversion. 1 atmosphere and 101.325 kilopascals. Both those numbers have an infinite number of significant figures. So I have 220, no decimal, and that has two significant figures just like the 2.2 atmospheres. I also have to convert the 72.8 degrees Celsius into Kelvin. And here's this conversion here into Kelvin. 72.8 has one decimal place, so it's significant in the 10th position. So after I add the 273.15, I am rounding such that I have a number that is significant in the 10th position. Fantastic. Now we're going to look at Gay-Lussac's mathematical equation. And here is the combined gas law, but I've highlighted where the volumes are, and we're going to negate those, get rid of those, because that is really the combined gas law. And since this is Gay-Lussac's law and volume is being held constant, we're going to get rid of that part. Okay? So, as always, we need to make a prediction. And what is being held constant here? Volume is being held constant. And we're going to come back to this here, but I hope you see that the 92.5 kilopascals is going to 220 kilopascals. So that's an increase in pressure. With an increase in pressure, I should have an increase in temperature because it's a direct relationship. So I'm rotating at that V right there. Okay, let's see if this holds true. I'm going to get rid of the volumes, and I have my Gay-Lussac's proportionality equation there. I'm going to rearrange this to solve for T2, and now I'm going to plug in the numbers as is appropriate. You should see that the kilopascals cancels out. I'm going to have Kelvin as my temperature units. I'm going to always look for significant figures. The 220 kilopascals has two significant figures. The 346.0 has four significant figures. That is trailing zeros with decimals in the number they count. And then the 92.5 kilopascals, that has three significant figures. So my ending answer here, rounded correctly, will have two significant figures. And here's my ending answer. and that is 820 Kelvin. And I'm going to go back to my prediction. That is rotating at that V. I'm increasing the pressure, therefore my temperature is going to increase. My temperature was originally 346 Kelvin, so I know that my temperature is going to be higher than that. 820 is a great representation of that. All right. And I am the Crazy Cat Chemist. That was the 8th video in a series of 16. Next time, I want you to look for the next video, and that is going to be on Dalton's Law. So look forward to Dalton's Law. I'll see you next time.